Welcome back to JVM Internals Crashcasts. I'm your host, Sheila, and today we're diving deeper into the fascinating world of garbage collection in the JVM. We're currently in Level 2 of our series, focusing on operational understanding of the JVM. In this episode, we'll be exploring different garbage collection algorithms, specifically serial, parallel, CMS, and G1. Victor, are you ready to help our listeners navigate through this complex topic?
Absolutely, Sheila. I'm excited to break down these algorithms and help our listeners understand how they impact Java application performance.
Great. Before we dive in, let's start with a quick quiz for our listeners. Here's the question. In a high-throughput, low-latency application running on a multi-core server, which garbage collection algorithm would likely be the best choice? Serial, parallel, CMS, or G1?
That's an excellent question, Sheila. It really makes our listeners think about the trade-offs between different GC algorithms and how they relate to real-world scenarios. The answer isn't as straightforward as it might seem, as it depends on various factors like heap size, application characteristics, and specific performance requirements. I'm looking forward to exploring this further in our discussion today.
Absolutely, Victor. Now, before we get into the specifics of each algorithm, could you give us a quick refresher on what garbage collection is and why it's so important in the JVM?
Certainly. Garbage collection, or GC for short, is the process by which the JVM automatically frees up memory that's no longer being used by the application. It's crucial because it allows developers to focus on writing code without worrying about manual memory management, which can be error-prone and time-consuming. The challenge lies in performing this cleanup efficiently without significantly impacting application performance.
That's a great overview, Victor. Now, let's start with the simplest GC algorithm, the serial GC. Can you explain how it works?
Of course, the serial GC is the most basic garbage collection algorithm. It uses a single thread to perform all garbage collection work, which means it stops all application threads during the collection process. This stop-the-world pause, where the application briefly freezes, can be noticeable in larger applications. Think of it like a solo cleaner tidying up a room, efficient for small spaces but potentially slow for larger areas.
I see. So it's simple but might not be suitable for all situations. When might someone choose to use the serial GC?
Great question. The serial GC is best suited for small applications with small heaps, typically less than 100 MB, running on single-processor machines. It's also the default choice for the client-side JVM on certain platforms. Despite its limitations, it can be very efficient in the right circumstances due to its simplicity and low overhead.
That makes sense. Now, let's move on to the parallel GC. How does it differ from the serial GC?
The parallel GC, as the name suggests, uses multiple threads to perform garbage collection. It's like having a team of cleaners instead of just one. This approach can significantly reduce GC pause times, especially for larger heaps on multi-core systems. However, it still causes stop-the-world pauses, just shorter ones compared to the serial GC.
Interesting. So it's faster, but still has some drawbacks. What about the concurrent mark sweep, CMS collector? That sounds more complex.
You're right, Sheila. The CMS collector is indeed more complex. It's designed to minimize pause times by doing most of its work concurrently with the application threads. Think of it as a cleaner who tidies up while you're still using the room, only asking you to pause briefly at certain points. CMS works in several phases: initial mark, brief pause, concurrent mark, concurrent sweep, and concurrent reset. Only the initial mark and parts of the final sweep cause stop-the-world pauses, which are typically much shorter than those of serial or parallel GC.
That sounds great for reducing pause times, but I'm guessing there's a trade-off.
Exactly. The main trade-offs with CMS are increased CPU usage, as it runs concurrently with the application, and the potential for heap fragmentation over time. It's also more complex to tune and can occasionally result in long pauses if it can't keep up with the rate of garbage creation.
I see. So we've covered serial, parallel, and CMS. That leaves us with the G1 collector. How does it fit into the picture?
G1, which stands for Garbage First, is the most recent and advanced of these four collectors. It's designed to be a replacement for CMS, especially for large heaps. G1 divides the heap into regions and focuses on collecting the regions with the most garbage first, hence its name. Think of G1 like a smart cleaning system that identifies the messiest areas of your house and cleans those first. It aims to provide more predictable pause times while still maintaining good throughput. G1 can do both young and old generation collection, and it can even evacuate live objects between regions to combat fragmentation.
Wow, that sounds quite sophisticated. It seems like each algorithm builds on the previous ones, addressing their limitations. Now, coming back to our quiz question. In a high-throughput, low-latency application on a multi-core server, which of these would likely be the best choice?
Great question to circle back to, Sheila. For a high-throughput, low-latency application on a multi-core server, the G1 collector would likely be the best choice. It's designed to provide a good balance between throughput and latency, and it scales well to larger heap sizes and multi-core systems. However, it's worth noting that the best choice can still depend on specific application characteristics and requirements. In some cases, a well-tuned CMS might still be preferable.
Thank you, Victor. That's a great explanation. To summarize for our listeners, we've covered four main garbage collection algorithms today. The serial GC is simple and efficient for small applications. The parallel GC improves on this for multi-core systems. The CMS collector aims to reduce pause times by doing most work concurrently. And finally, the G1 collector provides a balance of throughput and low pause times, especially for large heaps. In our next episode, we'll be diving into GC tuning and monitoring, where we'll explore how to optimize these collectors for specific applications. Don't forget to subscribe to our podcast and leave us a rating if you found this helpful. Until next time, happy coding.